Hello, and welcome back to another wonderful day. Today, we will be discussing sampling distributions of X bar, meaning sample means. Previously, we looked at sampling distributions of P hat, proportions. Here, we are going to compare a population distribution to its sampling distribution of X bar. On the left is the population distribution of household earnings in thousands of dollars. That is the population distribution. Notice that that population distribution is skewed to the right. Okay, not normal. It is definitely skewed. However, if you look at the right distribution, which is the sampling distribution, that is a sampling distribution of samples of size 100. And what you'll notice is that the mean of the population distribution is the center of my sampling distribution, which should make sense because we said that the parameter of a population is the center of its sampling distribution. What you will also notice is that this sampling distribution looks much more normal than the population distribution. So let's examine why that occurs. The sampling distribution of X bar will have a center or a mean of the parameter mu. So just like in the sampling distribution of P hat, the parameter was P, now we have a parameter mu, and that is the center of our sampling distribution. The standard deviation of our sampling distribution, which we call sigma sub X bar, is sigma over square root of n, where sigma is the standard deviation of the population and n is the sample size. Again, we can only use this formula if our 10% condition is satisfied because each sample has to be independent of other samples. Now, these facts about the mean and the standard deviation are always true no matter what the shape of the population distribution is. So the population distribution that we just looked at was skewed to the right. So even though that was skewed to the right, the mean and standard deviation of our sampling distribution could be found using these two formulas. Okay. So we have described the mean and standard deviation of a sampling distribution of sample mean X bar, but not shape. Right? We found the mean and standard deviation. So that's because the shape of the distribution of X bar really depends on the population distribution. So again, the mean and standard deviation do not depend on the population distribution shape. However, the shape of my sampling distribution does. In one important case, there is a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution. Okay, so again, if the population distribution is normal, then that means that the sampling distribution is also normal. Think back to proportions. In order to see if our sampling distribution was normal or approximately normal, we had to do n times p and n times 1 minus p. We don't have to do that here because we don't have a p, right? Now we're talking about X bars. So if our population distribution is normal, then our sampling distribution is also normal. But what happens if our population distribution is not normal? How can we find the shape of the sampling distribution? This is called the central limit theorem. The central limit theorem says that as long as our sample size is large, very large, then the sampling distribution will be approximately normal. So again, the central limit theorem says as long as our sample size is large, then the sampling distribution of X bar will be approximately normal. This is kind of similar to when we checked in proportions n times p and n times 1 minus p, because we said that n has to be large, and then we said, oh, how large? Well, large enough so that the expected number of successes and the expected number of failures were both bigger than 10. But now for means, we have this new theorem called the central limit theorem. And again, it requires a large sample size in order for us to say that the sampling distribution is approximately normal. So how large is large enough? Let's take a look. The top is a population distribution. Clearly, the population distribution is not normal. Okay, it's very not normal. So you got 3 clusters. It is very non-normal. The next thing that you'll see is a sampling distribution of sample size 2. Okay, so this is where I just took samples of size 2 from this weird population and I graphed the sampling distribution here. Then I took sample sizes of size 5 and I graphed its sampling distribution. And you can see just at sample size of size 5, we are starting to get a nice unimodal distribution. Here is sample size of size 10. Okay, it is a sampling distribution where samples are size 10. And now here are samples of size 25. And as you can see, as my samples get larger, my sampling distribution gets closer and closer to normal. So how big is big enough to consider it approximately normal? Well, according to the central limit theorem, we say that the sample size has to be at least 30. If the sample size is 30 or more, then no matter what the population distribution is, the sampling distribution will be approximately normal. Even if my population distribution looks super skewed one way or the other, if I'm taking samples of size 30 or more, my sampling distribution will be approximately normal. Okay? It's the normal or large condition for sample means. And it's different than the large condition for proportions, because in proportions, we can just do n times p and n times 1 minus p. Okay, so here is an image of our sampling distribution, where we have the center of our sampling distribution is our parameter, and then the standard deviation of our sampling distribution is the standard deviation of the population divided by the square root of the sample size. Let's do a couple of problems together. Let's make this full screen. That's good enough. Okay, so this says the height of a young woman follows a normal distribution with a mean of 64.5 and a standard deviation of 2.5. So the values that they give you are parameters, right? They give you the mean. I'll draw a circle. Let me get my tools. There we are. Okay, and so we have the mean and we have the standard deviation. So in part A, it says find the probability that a randomly selected young woman is taller than 66.5 inches. Okay, so here in part A, I'm selecting just one young woman. This part A is a question that you would see back in chapter 2, right? Where we have the mean and the standard deviation of our population. And we know that the population distribution is normal. And we know that because it tells us it follows a normal distribution. So it's stated in the problem. Okay, and what you'll notice is that you're going to start writing more paragraphs for your answers instead of just numbers, because you're going to have to explain your thinking to me in a problem. Okay, so since our population distribution is normal, our task is to find the probability that a single randomly selected girl, which we'll call X, is bigger than 66.5 inches. Okay, now because the population distribution is normal, I can go ahead and use a norm CDF. And the lower bound would be 66.5. The upper bound would be a very large number. The mean is 64.5, and the standard deviation is 2.5. And again, I have to label this, so it would be lower bound, upper bound, the mean, and the standard deviation. And when I put that into my calculator, the probability that X is greater than 66.5 is equal to approximately 0.2119, or 21.19%. Okay, this is a chapter 2 problem. I'm taking a single girl from the population. Now, let's look at part B. Part B says, find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches. So now, for part B, I have mu is 64.5. I have my standard deviation of 2.5. Now, these are my population mean and standard deviation. But now that I'm taking a sample size of size 10, I'm looking at a sampling distribution, because now I'm taking a sample size of size 10. Here, technically, I was taking a sample size of size 1. So now that n is 10, I need to find the center of my sampling distribution. And the center of my sampling distribution, which is the mu sub x bar, is also going to be 64.5. Okay, now I need to find the standard deviation of my sampling distribution. However, in order for me to use the standard deviation formula, I have to check and write down the 10% rule. So I'm going to say that we assume that there are more than 10 times 10 young women in the world. Doesn't say where I'm taking these young women from, so I'm going to assume it's the entire world. Okay, this is me checking my independence. Now, since this is true, we can go ahead and find the standard deviation of my sampling distribution x bar, which is just 2.5 divided by the square root of 10, because it is sigma over square root of n. Okay, our task is to find the probability, that x bar is bigger than 66.5. In order to do this, I would like to know if my sampling distribution is approximately normal. Well, since the population distribution is normal, the sampling distribution is also normal. And there it is, checking my normal condition. These are conditions that you're going to have to check all the time. So because my sampling distribution is also normal, I can go ahead and use a normal CDF to solve my problem. So norm CDF, lower bound 66.5, upper bound 9999, mean is 64.5, and standard deviation is 2.5 divided by the square root of 10. And when I'm labeling this, it'll be lower bound, upper bound, the mean of x bar, and the standard deviation of x bar. All right, these are different labels than what we had here, because this was for our population. These are parameters. These are for our sampling distribution. And when I use my calculator, I get a value of 0.0057, a much smaller number than what we got in our first, because here I was just selecting 1 woman. Now I want 10 women who average a height bigger than 66.5 inches. Now this problem, the population was normal. So we can just state that the population is normal. We didn't have to use the central limit theorem. In this new problem, you'll see that the population is not normal. So we're going to have to utilize the central limit theorem. So it says your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on the service records from past year, the time in hours that a technician requires to complete the following follows a strongly right skewed distribution. There it is. The population distribution is strongly right skewed. Okay, that's okay, because we're going to hopefully be able to use our central limit theorem. They give us the mean and standard deviation of our right skewed population. So I'm going to write that down, because I always write down what's given to me. The mean's 1 hour, and the standard deviation is also 1 hour. Okay. In the coming week, your company will service a simple random sample of 70 air conditioning units in the city. So I know I'm going to take a sample size of 70. You plan to budget an average of 1.1 hours per unit for a technician to complete the work. Will this be enough time? Is 1.1 hours enough? Well, let's find out. What is the probability that the average maintenance time, X bar, for the 70 units exceeds 1.1 hours? So our task is to find the probability that X bar is bigger than 1.1. In order to do this, we need to find sigma sub X bar. We can only find sigma sub X bar if my samples are independent of one another. In order to check independence, we gotta check the 10% rule. We assume that there are more than 10 times 70 units in the large city. Because this 10% rule is true, we can go ahead and find the standard deviation of my sampling distribution, which would be 1 divided by the square root of 70. Now, in order for us to use normal CDF, we gotta check to make sure that our sampling distribution is approximately normal. So, since n is greater than 30, according to the central limit theorem, which I'll call CLT, the sampling distribution will be approximately normal. Okay, not exactly normal, but approximately normal. That's different than the first one. The first example we did, the population was normal, so therefore the sampling distribution is exactly normal. This sampling distribution won't be exactly normal, it'll be approximately normal. So there's my sampling distribution. It is going to be approximately normal, so I can go ahead and use a normal distribution. Norm CDF. My lower bound is 1.1. My upper bound is going to be 9999. My mean will be 1 hour, and my standard deviation is 1 divided by the square root of 70. So this is lower bound, upper bound, mean of X bar, standard deviation of X bar. And when I use normal CDF in my calculator, I get 0.2014 or 20.14%. And that just means that there's a 20% chance that the average maintenance time for the 70 units exceeds 1.1 hours. Now, if I am the person who is in charge of this, I would think that that probability is too high, and you should probably budget for more than 1.1 hours, because there's still a 20% chance that your average is higher than 1.1. But that's just me. I'm a math teacher. I don't handle company decisions. Okay? And this would be your full answer, checking both conditions in order to use this formula and the normal CDF. Okay, I will see you all in class. Have a great day.